Good morning from Democritus one more time. I'm George Vekinis, and today we'll be talking about the strength of materials, specifically of strength of metals, and I will bring you back many years. We'll give you a little bit of historical background on this. About 20 years ago this year, in 2001, in September 2001, there was the infamous attack on the Twin Towers, the Trade Center in New York. Now, we're going to talk about a lot of people actually, after the attack, a lot of people developed some conspiracy theories and things like that. So I'm going to explain to you how the collapse occurred. So if we look at some original footage from that time, there is the moment of attack from there in the second tower. There is the explosion, and remember the explosion was now fuel, airplane fuel, plus the aluminum that the airplane was made of, which burns at a very high temperature. So after a few minutes, the tower started collapsing, and started collapsing uniformly, symmetrically. And a lot of people said, well, how is this possible? That looks like a controlled collapse, controlled explosion or something like that. Well, it's not controlled, it's uncontrolled, but it's exactly the way that we'd expect steel bars, reinforcing bars in a building like this to behave. So let's explain this now. We're going to do the experiment. We're going to show you in the instrument exactly how this could take place and exactly how steel loses all its load-bearing capacity as soon as it gets a little bit warm, a little bit hot. And remember that the towers, the temperature inside the building must have reached more than 1500 degrees. So a melting point of steel, but we'll show you that the effect starts at a much lower temperature. As low as 600, 650 degrees, this steel loses most of its load-bearing capacity. So, okay, there it is, there's the steel. I'm going to be using a steel bar like this. It's identical material, almost the same material as used for reinforcing buildings. And this is just a screw, but it doesn't matter. I've connected it onto the crossbar. The crossbar is pressing down onto the bottom platen. And I'm going to load it to about 1,000 kilograms, which is approximately what each bar is expected to be loaded to in a building like that, because they've got thousands of bars all around, of course. And so we're going to load it to about 1,000 kilograms, and then I'm going to heat it up and watch. We're showing you the graph of load against displacement, against the deformation, and as this thing will be increasing, watch what's going to happen to the load. Okay, so there it is. Let's start the experiment. And there it is. It's compressing. So the load is increasing. I've got it about 0.5 millimeter per minute, so it's quite a fast loading. And when it reaches about 1,000 kilograms, that means 10,000 newtons load. I'm gonna heat it up. I'm gonna start the flame now. At the moment, it's at about 150 kilograms only. And you can see how fast it increases now, because the load, most of the load is taken up by the bar. It's already at about 600 kilograms, 6,000 newtons, 7,000 newtons, 8,000 newtons, 9,000 newtons, and 10,000 newtons, 1 ton. And now I'm heating it up. And watch what happens. Immediately, the load increases suddenly because of expansion. The metal expands suddenly, which is a very important event. And then as the metal gets warm, at the moment a lot of the heat is dissipated, and suddenly the metal collapses. You can see the collapse. And you can see the deformation to the left, deformation of the bar. And of course, this collapse would be accompanied by a collapse of a whole building. So this is the important thing. This is what we call failure analysis. We have an event, we have an experiment, and we're trying to explain it. So the first event was, as the load, at that point over there, it was a normal loading, the building was still holding on. As soon as the temperature increased inside the building, the bars, the metal bars, started immediately expanding. So the first metal bars that would expand would be the ones on the floors. So they would expand against the side, the load bearing, the side vertical bars. And remember, those buildings were built mainly with steel. There was a lot of concrete, but mainly it was the steel that was the problem. So as soon as the expansion took place, all the bolts retaining the floors broke away. So the bolts internally where the lift shaft was, the bolts against the vertical, etc. The vertical bars started expanding immediately afterwards as well because they got very hot. And again, if there were any bolts remaining, they would collapse. So remember what happened. So the expansion was in all directions, and at the same time, the metal was actually getting weak. So there was expansion, the bolts, the retaining bolts broke away, there was a weakness of the steel, and because of the bolts all breaking away and the weakness of the steel, very soon afterwards, as soon as it reached a certain temperature, and the temperature of the steel now on the right side was maybe about 800, 900 degrees, on the left side it was only 600, so all the steel bars, the vertical steel bars, collapsed inwards, or at least collapsed, and the whole collapse of the building was happened completely symmetrically. So this is the way that this is explained, and it's exactly what we'd expect when you set a fire, a symmetric fire within a building. Now once many floors, 10 floors or something like that, collapsed, then there was a domino effect. All that load suddenly was taken up by the bars below, and of course there was an impact, and the impact actually caused the bottom floors to collapse as well. As soon as the top floors, 10, 20 floors collapsed, then the other ones were taking up the impact. And that's what failure analysis. In failure analysis, we use ideas from physics, we use ideas from material science, materials engineering, and we try to explain nature or any event or any catastrophic event like this. And I hope one day one of you decides to become a physicist or a material scientist or materials engineer, and you'll be able to explain the same way. So everything is explainable. There's no conspiracy. As far as we understand, it's completely understandable and completely explainable what happened then. So until next time, from Demokritos, have a good day and enjoy your lessons.